So, we will discuss today the continuity of functions. We have already seen how to define the functions. It is basically a mapping a rule from a set A to a set B, such that each element of A we can have a one unique element in B. Then functions is well defined. If there are more than one values of A, then we say it is not well defined, of course, function. However, when corresponding to each value x, we have one value, then it is a single valued function, and for each x, if there is more than one values of the images, more than one images, then we say it is a multi-valued function. Say for example, f x is the root x, there for each real x, positive real x, we have two values. So, it is a multi-valued functions. So, we will include all sort of the functions, whether it is a single valued function or multi-valued function. And when we say f x is a real valued function, it means that values of the f x lies in the real. So, let f x be a real valued function. By the domain of f, we mean domain of f, we mean the set of those real numbers R, set of those real number x belongs to R, such that the f x is well defined at this. Means f x should not be infinity or minus infinity, or the functional at x and it must be a finite value well defined. Normally, the domain of f, in general, the domain of f normally we consider either a open interval or maybe a closed interval or maybe a semi-closed interval, say like this, or even the entire real line R. So, it depends on the function where it is defined. We are not, and the set of those values of x is the range of f. Range of f means those y's such that there exists some x, it's such that f x equal to y for x belongs to the domain of f. Okay. So, all the images set is the range of the f. So, this much we have. Now, the domain of f the function, when we say the function is defined over a domain A, then it is not necessary that function, the domain will be a continuously defined like a b. It may be in the breakup form. Maybe the function may not be defined, same function may not behave, may not be defined over the entire domain. It may be several functions can be take up over the domain of the f. For example, if we say f x is say 0 when x is 0, say f x is equal to lying between say 1 by n plus 1 less than x less than equal to 1 by n, where n is an integer greater than equal to 2, say, then the value of this is defined as the functional f x is defined by 1 by n. So, in the interval when it is lying between 1 and 2, 1/2 less than x less than equal to 1, the function is defined suppose 1. So, this is also a way of defining the means a function may be take up of this type of also, where the interval, the domain of definition is from 0 to 1, but it is not the same function. By means of the same function, we are not defining over the interval. What we are doing, what we have here is over these several parts of this interval 0 1, this is 0 1 interval, we have a different form of the f at different points, or all even at different subintervals like this. So, this will be the. Now, there are different types of the functions which we come across, the like the rational types of real valued function or types of functions which we will come across. The first may be a rational integral function, a rational integral function, or polynomial. We can also say it is or a polynomial. which is of the form like a naught plus a1x a2 x square plus an x to the power n, where the coefficients a naught, a1, a2, an, these are all constants, real constants, okay, and n is a positive integer. Positive integer belongs to n. So, this is also a functional, and we denote by Pnx, a polynomial of degree n. Another type of the function which we come across about the rational functions. Rational functions, a function f x which is of the form p x by q x, where p x is also a polynomial say of degree n, q x is a polynomial of degree say m, but phi of m x is not 0 for any x belongs to the domain of f. For every x belongs to a, phi m x is not 0. Then such a function we call it as a rational function. And then a third type of the function which we can approach as algebraic function. Algebraic function is a function which is or which can be expressed as the root of an equation of the form, say y to the power n plus f1 y to the power n minus 1 plus f2 y to the power n minus 2 plus fn equal to 0, where these f1, f2, fn, these are rational functions of f, where these f1, f2, fn are rational functions of x. So, the roots of this equation will be a function, because these are all rational functions, coefficients are rational functions. So, the roots will be a function, and that function we call it as algebraic functions. Then transcendental function are those functions which are not algebraic, is that function which is not algebraic function, So, transcendental functions are there. Now, in this case we have seen so many examples like logarithmic function, and then trigonometric functions like and then exponential functions. All these functions we will come across for this. So, we will discuss in general first the continuity of these type of functions, and then we will see that these functions which are smooth, continuous, and also the some uniform continuity will also be tested, will be more useful to develop further the theory. Okay. So, let us come to now, before going for this say definition for continuity, we will also we require the bounds for it. So, let y or the bound of the functions, In fact, this is when we say the function f x is bounded, when we do we say. So, let f y is equal to f x be a real valued function defined over its domain of definition. whatever, whether it interval or maybe a union of the disjoint intervals and like this intervals. The set the values of y, the values of y corresponding to the different values of x. So, this will form a set, the values of y corresponding to the different values of x. So, if the set of the values of y corresponding to different values of x, if it is bounded, if the set of values of y corresponding to different values of x, where the x belongs to the domain of f, is bounded, then we say the function f x is a bounded function. It means that is mod of f x is less than or equal to some constant, that is there exists some m greater than 0, such that this is true for all x belongs to the domain of f. What is f x? F x is y basically, the value of f at the point x denoted by y. So, if the set of all values of f x, if this set is a bounded set, then we say the function f is a bounded function. And in the similar way, the upper and lower bound of this set, the upper and lower bound of this set, upper and lower bound of this sets are the upper and lower bound, upper and lower bounds of the function f x. That is, if you want the upper bound of f x, then find out the all images and then among these images find the upper bound. So, that upper bound will be the upper bound for f x, similarly the lower bound for f x, like that. If this upper bound is finite, fine, otherwise this may be unbounded set. If the upper bound we are not able to get m to be finite. Okay. Now, one more results which we require here, that is a theorem given by Weierstrass. The theorem says, if a function f x be defined in the interval a b, open interval a b, then there exists at least one point in the interval a b, such that in an arbitrary small neighborhood of this point, the least upper bound of f x, the least upper bound of f x, least upper bound of f x is the same as in a b. So, what he says is, if suppose the function be defined, this is a function, suppose this is interval and the function is defined everywhere at this, everywhere it is the function is well defined. Then there exists a point, say x naught, in the interval a b such that in a very arbitrary small neighborhood if I choose, then this function will have the same upper bound as it is in over the entire thing. Say if I choose this function, suppose this is only function, suppose I take this function, suppose I take. Okay. Now, you see the upper bound maximum value is attained at this point. Okay. Now, we can find a very small point x naught, so that in an arbitrary small neighborhood, the upper bound of the function f a is the same as the upper bound of the function over the entire range a b. That is what its result says. The proof is obviously the function is throughout well defined function. The proof is very simple. Suppose the upper bound of this is suppose m. Okay. Then what we do? Let us find that bisection of this interval such that we get this. Let m be the upper bound of this. Okay. So, let m be the upper bound of f x over the interval x belongs to a b. Okay. X belongs to a b. This is an upper bound for this. Say least upper bound we can say is this. If it is closed interval, then we can say least upper bound of this in the closed interval, let it be, it's okay, no problem. Okay. Now, this interval is given, we divide this interval into two parts of equal length. Now, we pick up that interval in which that least upper bound occurs. Okay. Suppose we have this say this curve, suppose like this, suppose this curve is there. So, what we do is we divide this into two equal intervals and then we pick up the interval a1 b1, which is divide AB interval into two equal intervals of length b minus a by 2 each of length this each of this length. So, let call that interval, pick up that interval in which the least upper bound is there. So, obviously, here a1 b1 in this interval this upper bound lies. Okay. So, this a1 b1 call it this interval a1 b1 in which the function f x has an upper bound, call it this. Now, this a1 may coincide with a or b1 may coincide with b depending on the function. Now, further again divide a1 b1 interval into two equal intervals of length equal to b minus a by 2 square, and then pick up this, call that interval, pick up the interval say a2 b2 in which the function f x has an upper bound. So, you are further dividing this into, you are further dividing it into two. So, now I am picking up this we call it a2, this is b2, because in this only the upper bound lies. Continue this process. So, if I continue this process, what happens? We are getting in this process, when you continue, you are getting the sequence of the points a1, a2, an such that a is less than equal to a1, less than equal to a2 and so on, while b is greater than equal to b1, greater than equal to b2 and so on. So, A is an increasing monotonic increasing sequence, B is a monotonic decreasing sequence, but the upper bound of A cannot exceed by B 1 and lower bound of this, when you take the B 1, B 2, B n, all these things, the lower bound of this will be again when you take B 1, B 2, B 1 is an upper bound here, is it not? So, this is bounded above, this is bounded below, and below will be at the most B. B. Okay. So, this will be the both are. So, these are the monotonic sequence, these are bounded monotone sequences, and we know the bounded monotone sequence of real numbers or rational numbers, they are all convergent. So, they will converge. So, they converges. So, these are convergent sequence. So, these are convergent sequences. Hence, A n will converge to a point, B n will converge from there. So, we get from here A b. So, A 1 less than equal to A 2 less than equal to A 3 n, B greater than B 1 greater than B 2 and so on. So, A n will go this side, B n go this side. So, a point x naught can be obtained where the limit of this will coincide. Okay. Why? Because at the nth step what we get, the difference between B n minus A n will be half to the power n B minus A. So, as n tends to infinity, this difference is very, very small. Therefore, as n tends to infinity, both the sequence A n and B n will tend to the same limit, and that limit point is our A, say A x naught. It means there exists an x naught and a neighborhood around the point x naught will be there, in which the upper bound lies. Okay. So, the point x naught, the point clearly, the point x naught has the required property, that is for any sign, neighborhood delta of x naught contains the interval n comma b n for large n, so the least upper bound of the function f x in delta is m. That is what is proved. Okay. So, this is basically is proved, and assuming the function is well defined at each point of this. So, the continuity is obviously is taken in consideration here. So, now looking up there, now we come formally the definition of continuity. So, there are two ways of defining the continuity. One is given by the Cauchy, another one is given by Henne. So, Cauchy has taken in the form using the epsilon delta definition, that in terms of the intervals, while that Henne has defined the continuity of the function in terms of the limit of the sequences. But both these concepts, both the definitions are basically equivalent definition. So, we will see first what are these definitions, and then we will justify that these two definitions are basically an equivalent definition. So, let us see the continuity of the function of functions. So, first the definition by Cauchy's definition. What the Cauchy's definition? Let the domain of continuity, let f x be a function v of real valued function function define over a continuous interval AB. Of course, here we are taking a continuous interval, but it may be partly function will also be defined with a different way. So, over a continuous function interval AB, and let y equal to f x be the given values of the function at this interval. Then the function f x, is said to be continuous at a point x naught in the interval a b if for a given epsilon greater than 0, or if corresponding to an arbitrary arbitrarily choosing positive number epsilon, however small may be, Okay. Another, there exist corresponding to this, there exist a positive number delta which depends on epsilon as well as on the point x naught, such that the modulus of f x minus f x naught is less than epsilon, provided mod of x minus x naught is less than delta. Okay. It means what? The meaning is this: a function f is continuous at a point x naught if for a corresponding to a assigned arbitrary choosing positive number epsilon, there exists a delta, depends on epsilon, so such that this condition holds. It means that if we take epsilon is given, then we can find out a neighborhood of x naught, say x naught minus delta and x naught plus delta. A neighborhood can be obtained with respect to this given epsilon, with respect to the bound which is given here, such that the image of any point x will always fall within this range. That is, here is say f x naught, then the range fluctuation of this will be f x naught minus epsilon, f x naught plus epsilon. Because mod of f x minus f x naught less than this implies the f x lies between f x naught minus epsilon and f x naught plus epsilon, and this we mean that x lies between x naught minus delta and x naught plus delta. It may, so if f is continuous, then a neighborhood of the x naught exists such that image of any point x in this neighborhood will always satisfy this condition, that is, will always fall within this 2 epsilon bits of that step, whatever the point you choose. If so, then we say it is a function. It means the total fluctuation, of the function f x in the interval x naught minus delta to x naught plus delta is what? The is basically the difference between these two, upper and the lower bound. So, x naught plus epsilon minus f x naught minus epsilon, and that is equal to 2 epsilon. So, if this fluctuation is less than 2 epsilon, which is less than this 2 epsilon, very small number, then we say the function is continuous. So, this is also considered as a necessary condition for the function. So, we can say, important note, we can say the function f x, is continuous at a point function f x is continuous at a point if a neighborhood of the point can be determined in which the fluctuation is as small as we please, So, this is also considered as a necessary condition, because if this does not satisfy, the function cannot be continuous function. For example, suppose I take this graph, say this is our graph, point x naught is here, function f is this. Now, however small with this given epsilon, say with this given epsilon, I take this point is say f x naught. So, this point is f x naught minus epsilon, this point will be f x naught plus epsilon, and here this is f x naught. So, for this epsilon, this is the width 2 epsilon. For a given epsilon, if we get, there must exist an interval neighborhood around the point x naught such that the fluctuation should not exceed by epsilon. But what happen if it suppose I take this neighborhood, okay, this is our neighborhood like this. So, as soon as you take this point, say here, this is point here, as soon as this point, the corresponding image of this will go here. It means the fluctuation may exceed by 2 epsilon. So, it cannot be made as small as we please, and this is because there is no continuity of the curve at this point x naught. So, such a function will not be considered as a continuous function. So, that is important, that is why we say this is a case of discontinuity, continuous function, case of discontinuity, okay, because of this thing, clear. So, that is why it is necessary condition. Now, as a corollary of this, of course, we further extend this. Suppose a function is given over a closed interval, the domain of definition is closed interval, and when we say the function is continuous over the closed interval, then what we do? We take the open interval first, and then at the point a and b also we test it. But before a the function may not be defined, after b the function may also not be defined. So, we have to modify our definition of the continuity at the end point of the interval. So, we say the function is said to be is said to be f x is said to be continuous on the right at x naught. Suppose this is x naught, on the right means this side, this side, okay, on from the right hand side, this is right, on the right of x naught, right on the right at x naught, on a function is said to be continuous, right, if the fluctuation of the function, in a neighborhood of x naught, if the fluctuation of the function in a neighborhood of x naught on the right that is x naught plus delta, this is a neighborhood on the right of this. If the fluctuation of the function in the neighborhood of x naught on the right of x naught on the right is as small as we please, then we say the function is continuous at a point x naught from the right hand side. Similarly, the function is said to be continuous on the left, the function f x is said to be continuous on the left of x naught if the fluctuation of the function in a neighborhood of x naught on the left means that is x naught minus delta x naught on the left is as small as we please. So that's the important one. Okay. Yeah. So now we can define the function over the continuity in the interval. So we define as a continuity of the function, continuity in the interval. The function f x defined for a continuous interval a b. Continuous interval a b is said to be continuous in the interval a b, in that interval a b, that is at each point, if it is continuous at every point of the interval. Okay. If it is a closed, similarly we say f x is continuous in the closed interval or over the closed interval a b, if it is continuous at every point of the open interval a b, and continuous and continuous on the right at x equal to a and continuous on the left at x equal to b. Then we say the function is continuous. Okay. Now, let us take an example which is using the epsilon delta definition. Suppose prove that f x equal to sin x is continuous function, is continuous say over the interval 0 to pi by 2. In fact, it is continuous everywhere because it is a periodic function. So, we can say it okay, say 0 to pi by 2 is continuous. In fact, it is continuous over the entire real line R, over the entire real line R. So, the proof is simple. Suppose epsilon r is given greater than 0 is given. Okay. We have to identify delta depends on epsilon. So, that the mode of f x minus f x naught less than epsilon is less than epsilon provided x minus x naught less than delta. So, consider this, consider mode of f x minus f x naught, where let x naught be a point in this interval suppose. Okay, or all. Then what is this? This is sin x minus sin x naught, but this is equal to 2 times sin x plus x naught by 2 into sin x minus x naught by 2 mode of this, which is less than equal to. Now, sin of this thing is a bounded function bounded by 1. So, this is less than equal to 1 and this sin will be less than equal to mod x minus x naught. Why? Because mode of sin, because the sin x is less than equal to x for x lying between 0 and pi by 2. Sin 0 is 0, sin 90 is pi by 2, or even 0 to pi it will help. Okay, so, any interval you can just say this is. In fact, this can be extended for any x real x. Okay, so, this is 2. Now, if I take the f delta, so I choose delta equal to epsilon. So, if this is less than delta, obviously this will less than epsilon. So, this shows that sin x is continuous at x naught, but x naught is an arbitrary. So, it is continuous everywhere, and even if we take interval sin x is basically is continuous over any closed any open interval a b or in the real line. In fact, this one can prove easily. So, this is one of the example which we have I have chosen. Now, corollary there is one small result which we call the corollary. If f x is continuous, if f x is continuous at a point x naught and f x naught is positive, then f x is positive over the entire interval x naught minus x naught plus delta. Means if the function is continuous at point and at the point x naught it is positive function, it is a positive function, graph is up, then we can find a neighborhood where the function will remain positive. Okay. The reason is because it is continuous. So, this condition is satisfied for a given epsilon r greater than 0. There exists a delta depending on epsilon r such that this is true provided mod of x minus x naught less than delta. So, when the x lies between this, then what happen? This shows the f x is lying between f x naught plus epsilon r greater than f x naught minus epsilon r. So, if I choose epsilon r to be half of f x naught, then obviously f x will always be greater than the will be basically half of f x naught. because of the left hand side which is positive. So, this is true for all x belongs to the neighborhood of x naught, neighborhood of x naught with the radius delta. Okay. So, this now Hannibal definition for n, definition of continuity given by Hannay. This is given in terms of the sequence. So, what he says, let x1, x2, xn, x1, x2, xn be a convergent sequence of real numbers, say of real numbers or points on the real line in the given interval a b, in the given interval whose limit is say a, limit is say a. The function f x, by definition of the function f x is said to be continuous, at a point a if for every such sequence, for every such convergent sequences xn, every such convergent sequence xn, the sequence of their functionals value, sequence of numbers, functional value means it is in numbers now, f of xn, this is real numbers, converges to f of a. That is, the meaning is f is continuous at a point x equal to say x equal to a if the limit of the function f x when x tends to a exist and coincide with the functional value at a. This definition is if and only if. In fact, this is the definition given by this. It's okay if this condition. Okay. In fact, it's part if and only if also function b. So, what it says is that if we take a sequence xn which converges to a, then f of xn will go to f a. That is the definition given by the Hannay. Now, these two definitions are basically equivalent definition. The equivalence of Cauchy's and Hannay's definition of continuity. So, let us assume the function is continuous, assume f x is continuous in according to Cauchy's. It means that is for a given epsilon greater than 0, there exists a delta depending on epsilon such that mod of f x minus f x naught continuous at x naught. F x naught is less than epsilon provided mod of x minus x naught less than delta. Suppose this is true. Okay. Now, let us consider a sequence xn, a convergent sequence xn having the limit a, means xn sequence converges to a. So, by definition, modulus of xn minus a is less than say delta for all n greater than equal to say capital small m, say, because limit of xn is a. So, xn minus a will remain less than after a certain stage. But if xn lies itna, this implies that xn lies between a minus delta and a plus delta for all n greater than equal to m. And for such point which lies in this one, satisfy this condition. So, using one what we get is mod of f x n minus f x naught, yes, continuous at x naught. So, here x naught actually I have taken a limit is x naught. Let us take x naught here. So, x naught. So, here is x naught, this is also x naught, because in place of this. So, f x naught, this will remain less than epsilon r for all n greater than equal to m. Therefore, limit of f x n as n tends to infinity is f x naught. Hence, Henne's definition follows. Hence, by Henne's definition, f is continuous at x naught. Conversely, suppose Henne's definition, suppose f is continuous at x naught in accordance to Henne's definition. Suppose this. Suppose we say it's continuous in accordance with, but Cauchy's definition is not. Cauchy's definition is not satisfied. That is, for a given epsilon r greater than 0, for a given epsilon r greater than 0, there exist points, in the interval, say x naught minus delta, x naught plus delta, for which the fluctuation mod of f x minus f x naught exceed by any given number epsilon, howsoever small delta may be. So, what do you mean by this? This means if you take a sequence which is in this, okay, then all these sequence. So, let us take a consider a sequence delta n of decreasing nature, which decreases to 0, converges to 0, such that sequence delta n will converge to 0, such that, and x n be a point belongs to this x naught minus delta n, x naught plus delta n. If we take this point in this sequence of the point in this interval, then according to the second implies that mod of f x n minus f x naught will greater than equal to epsilon. This shows the limit of the f x n as n tends to infinity, as x tends to x naught, that is n tends to infinity means x n tends to infinity is not equal to f x naught. So, function f is not continuous at x naught. All this contradicts the definition of this. Therefore, this assumption that Cauchy definition is not very satisfied is wrong. Therefore, okay. Thank you very much. So, this was the equivalence of this.